This thing in this class sounds like my sixth period class. All right. We're going backwards a little bit to 2.7. We're going to talk about graphing rational functions. And the stuff we talk about today would be on the no calculator portion of a test. So we want to be able to do some graphing without plugging it into our calculator and looking at the graph on our calculator. It's always good if we can visualize a function a little bit without having to rely on our calculator. Oh, did I tell you I dreamed that I was weightless last night? I dreamed I was weightless. I was like OMG. Well, we decided in my last class that since gram is a measure of mass, it should have said I was massless, right? To be technically correct. All right, graphing rational functions. So we have all the tools that we need. So our tools for graphing. We have a rational function, f of x equals n of x over d of x. And n of x and d of x are polynomials. So our tools for graphing. One, we can find the x-intercepts. When we're graphing the function, it's always nice to know where across the x-axis. Well, how do we do that? A function, where does the function, how do we find when the function crosses the x-axis? Yeah. When n of x equals 0, we want the function to equal 0. Well, this function is going to equal 0 when n of x is 0. So finding zeros of polynomials is what we've been doing basically all of chapter 2. So that's part of what we do for graphing, find the x-intercept. We can also find the y-intercepts. And how do we go about that? What is true when our graph crosses the y-axis? X is 0. We plug in x equals 0 to find our y-intercept. We can also find our vertical asymptotes. I'll write VA. How do we find the vertical asymptotes? Yeah? We want to find when d of x is 0. So we're finding the zeros of the denominator. And that's going to give us our vertical asymptotes. Horizontal asymptotes. I should say horizontal asymptote. There can just be one. So I'm going to say HA. Have you ever heard of the movie Highlander? Movie or TV series? That was a big line from that. There can be only one. There can be only one horizontal asymptote. How do we find the horizontal asymptote? And we have our rules, our various rules. I'm just going to write, we use our rules for HA. And the rules have to do with comparing the degrees of n of x and d of x. So we have the different cases for the horizontal asymptote. And once we have that, the other thing that we're going to do to complete our graph is we're going to plot points. And we want to plot points between and beyond the horizontal asymptotes. The vertical asymptotes. So we want to plug in a few points to get the shape of the graph. And between vertical asymptotes, the rational function can do various different things, so we want to make sure we get the right shape. So we plot some points, and I'm going to put one other thing. Our function can cross horizontal asymptote. It cannot cross vertical asymptotes. Because remember, the horizontal asymptotes, really what they tell us is about the end behavior, what happens eventually. In between, function can do all kinds of things. All right, so what I want to do, we're going to go through 3 different cases. We're going to plot a couple of different rational functions, and then at the end we're going to talk about slant asymptotes. One case when we don't have a horizontal asymptote. We'll talk about how we can find a slant asymptote. All right, so we're good with all of our tools. Okay, let's start with a nice rational function. F of x equals x plus 1 over x. And we want to, for all of these, we want to sketch a graph. It doesn't really matter how we go about, what order we find our things in. One thing we have to be careful of is if we have a vertical asymptote, and that also turns out to be where we think there's an intercept, or a hole where we think there's a vertical asymptote, so we have to be careful of those things. So let's start with our vertical asymptotes here. So for this rational function, what's going to be our vertical asymptote? We want the denominator to be 0, so our vertical asymptote is the line x equals 0. So we don't want to say vertical asymptote is 0. It's a vertical asymptote is the equation of a line. Horizontal asymptote. And that's the only one, because that's the only thing that makes the denominator 0. Y equals 1. Our degrees are the same. Degree of the numerator is 1. Degree of the denominator is 1. So the horizontal asymptote is the ratio of the leading coefficients. Y equals 1. X-intercept. So we find the x-intercept when the numerator is 0. So we get at x equals -1. And on our graph, that's going to be the point, -1, 0. Y-intercept. So for our y-intercept, what do? Plug in x equals 0, but what's happening at x equals 0? We have a vertical asymptote. We can't have an asymptote and an intercept at the same place. So there's none. Because x equals 0 gives us a vertical asymptote. Yeah.
If you would have found like the x and y intercepts first and then the vertical asymptote, like is it always you'll choose that there can't be an intercept instead of a vertical asymptote?
Yes. Because the asymptote, with the vertical asymptote means, essentially it means a function doesn't even exist there. So it can't be an intercept if the function doesn't exist. Okay? All right, so this gives us enough to start our sketch. Then we'll plot some additional points based on our sketch. So we have a vertical asymptote at x equals 0, so that's the y-axis. We have a horizontal asymptote at y equals 1. And we have an x-intercept at -1, 0. So we know graph is somewhere over here. So what we have to do is find out over here, does the graph, is it down here, is it here, over here, what does it do? So I'm just going to plot some. So we're just going to plot some points. So let's plot a point for, I'm just going to calculate here, f of 1. I'm just going to plug in 1 here, and we get 2 over 1. So up here we get a point at 2. And I'm going to guess, just because that point is there, that my function is going to do this. I can plot another point if I'm not sure. F of 2, we get 3/2. So it's getting closer to the asymptote there. If we weren't sure, we could plug in f of 0.5. We'd get 1.5 over 0.5, which is 2 times 1.5, which is 3. So there it goes up to there. So I would say that tells me that my function is going to do this. And I know it's not going to cross the horizontal asymptote because x plus 1 over x, the numerator is always bigger than the denominator. So it can't get anything smaller than 1 as we go out, as we go out this way. And I'm going to guess, just based on this, then that my function does that. But I'll plot a couple of points just to make sure. Over here, f of -2, plug in -2 there. I get a -1 over -2, which is 1/2. So I get a point like that. So I'm going to say that's enough to tell me that my function is going to do this. It can't cross the vertical asymptote, so it's just going to go down here. If you weren't sure, you could plug in a couple of other points, and you would see that the function gets closer and closer to that horizontal asymptote there. Yeah.
So do you start measuring from the x-axis or the horizontal axis?
I just plot points. So you want to plot points if you're on the next one. We'll have our vertical asymptote not on the y-axis, and then I would pick points based on where the asymptote was. So if this asymptote was at 5, I'd plot some points over here at 6, 7, 8, and at 4, 3, 2. Does that make sense?
Yeah, but so for like the
these that's on the x-axis.
Yeah, but so you start counting from the bottom, even though it's like 3 lines up.
Oh,
or it's like that's just.
Then this is not to scale.
You still use
right.
the axis. Okay.
Yeah, this is just approximately. So this is approximately 1. This is approximately 1. That would be approximately 2. So yeah, I didn't mean to draw it so that two lines equaled 1. I just kind of eyeballed it. And if you drew your graph like this, if you sketch a graph like that, I'd be fine with it. It doesn't have to be beautiful and perfect. Okay. Are we good there? So that's a nice rational function. Let's look at one with a little more stuff going on. Still sketching a graph. F of x this time is x minus 2 over x squared minus 2x minus 8. So what's the first thing we're going to want to do here? Factor the denominator. So we want to factor, if we can, to find our zeros. So we get x minus 2. This one factors nicely. X plus 2 and x minus 4. And I would check, first thing I would check here when you factor is to make sure you don't have any holes where the numerator and denominator are 0 at the same time. So I don't have the same factors in the numerator and denominator, so I don't have any holes. When you find a hole, A hole is only a hole. A hole can't be an asymptote. A hole can't be an intercept. A hole is only a hole. All right. So let's find our vertical asymptotes. We're going to have two this time. Where are our vertical asymptotes? X equals -2. We want to find where the denominator is 0 and x equals 4. Horizontal asymptotes. Horizontal asymptote, sorry. We'll look at this one. The degree of the denominator is bigger. So what does that tell us about the horizontal asymptote? You remember? So y equals 0. And what we're saying, the reason that is because as x gets really, really big, this x squared is going to make the denominator bigger than the numerator. So we keep dividing by a bigger and bigger number. When you divide a number by a bigger and bigger number, it gets smaller and smaller and smaller and smaller. So as the x gets really big, our function gets closer and closer to 0. X-Intercept. What's going to be our X-Intercept? X equals 2, so it would be the point 2, 0. So we know it crosses the x-axis there. Y-intercept? Plug in x equals 0, and I get -2 over -8. Or is it do I get negative? X equals 0, -2. Get 1/4, right? Y equals 1/4. And if we want to write it as a point, that would be 0, 1/4. All right, we have enough to start our sketch, but we need to do a little more work with this one because we have these two vertical asymptotes. And we'll plot our points once we have our asymptotes plotted in there. All right, so at -2, I'm going to say that's -2. And at x equals 4, so that's about x equals 4. And our horizontal asymptote is at y equals 0. And we have an x-intercept at 2, 0, like so. And we have a y-intercept at 0, 1/4. So something like this. All right, so what we need to do now, our function could go here, 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 between the asymptotes. Because we have this intercept here, I'm going to guess it could either do a U shape there, or it could do kind of an S shape there. So we need to plot some points to decide what it does. So let's plot, this is at 4, so let's find f of 5. So I'm going to plug that in here. F of 5 is 5 minus 2 is 3. I get 25 minus 10 minus 8. Is that bigger or smaller than 0? Is it positive or negative? Positive. I'm going to say that's greater than 0. So I know at f of 5 my function is here somewhere. It can't cross the vertical asymptote. I could plot f of 6. So I get 6 minus 2, 4 over 36 minus 12 minus 8. F of 6, is that positive or negative? Positive. Well, it's going to be smaller because we get 36 minus 12 minus 8. So f of 6 is going to be like so. So I'm going to say this function does this. And we know it's going to stay positive because if x keeps getting bigger, our numerator is always positive, and we get this big squared, and the 2x minus 8 isn't enough to make it negative. So it's going to stay positive. It doesn't cross the horizontal asymptote. All right, so over here it could do this or it could do that. So let's plot a couple points. F of, where's this negative 2? Let's do f of negative 3. F of negative 3, so I get negative 5 over 9 plus 6 minus 8. Is that positive or negative? This is going to be positive, so that would be negative. So f of negative 3 is down here somewhere. So I'm going to say this function does that. And we could see that this number is always going to stay negative, because when I plug in a big number bigger than negative 2 in the negative, the numerator is always negative, but the denominator is always going to stay positive. So I always get a negative number here. So my function does that. Now we just need to see, does it make a U shape or an S shape? Because we know it can't go up and back down because there aren't any other intercepts. So it either has to do this or it has to do this. Oh, they can go in the desk. So I'll leave them in there. All right, so this is 2. Let's plot f of 3. And all we're really worried about for f of 3 is it positive or is it negative? So f of 3, 3 minus 2 is 1, 9 minus 6 minus 8. Positive or negative? Negative. So f of 3 is down here somewhere. So that function is going to do that. Kind of looks like a cotangent function between its asymptotes. There. Yeah.
So the horizontal asymptote only applies to the ones on the end? Like
Yes. Yeah. Because the horizontal asymptote is really, all it's really telling us is what happens eventually. What happens when x gets really big or really small. You could usually write just do the line for the entire thing, but really it only matters way out here. All right, questions there? And if you're not sure how these behave, plot a few more points. Pick nice points that are easy to calculate. I wouldn't try to calculate 2/3 here. Plug in x equals 2/3. That would be kind of messy. So plot some more points. If you know things are going bad if you try to graph rational functions by making a table of values, because you end up with points all over the place and you're not sure how they connect. So you need to use a little bit of what you know about the asymptotes and that kind of thing to help you graph your functions. All right, let's talk about slant asymptotes. The other term for slant asymptotes are oblique asymptotes. Oblique just means side, sort of. All right, so I want to look at an example. On a quiz or a test, I'm not going to ask you to graph a rational function with slant asymptotes, but I would ask you to find the slant asymptote. So for example, but we already know how to do it. We just don't know that we know. We just need a reminder. X squared over x minus 2. So if we use our horizontal asymptote rules, we would say, well, the degree of the numerator is bigger. It does not have a horizontal asymptote. I'm going to say no HA. But the degree of the numerator is 1 more than the degree of the denominator. If the degree of n of x is 1 more, than the degree of d of x, we have a slant asymptote. So we don't have a horizontal asymptote, but our asymptote slants. How are you going to guess? How would you guess that we're going to find it? What if we had a fraction with numbers and the numerator was bigger than the denominator? What could we do with those two numbers to rewrite the fraction? We had like 27 thirds. What do we do? What do we do with a fraction like 27 thirds? Yeah, we reduce it, and by reducing, what are we doing when we reduce? We're dividing. Yes, we divide. To find it, we use long division. So let's do this division. We're going to divide x minus 2 into x squared plus 0x plus 0. Putting my placeholders in there. And then we do our division. What do we have to multiply x by to get x squared? X. We multiply x squared minus 2x. Subtract. Those go away. I get 2x plus 0. Bring that 0 down. What do we multiply x by to get 2x? Plus 2. Multiply. 2x minus 4. And then I subtract. And I get my remainder is 4. The slant asymptote is the part that's left up here. So we would say y equals x plus 2 is the slant asymptote. And the reason is this tells us that x squared over x minus 2 equals x plus 2 plus 4 over x minus 2. As x gets really, really big, what happens to this fraction? We keep dividing by a really, really big number. It gets really, really small, right? As x gets really big, this fraction gets so small that's really not important. And the only thing that tells us about the function is that x plus 2. So that's going to be our slant asymptote. So y equals x plus 2 is the slant asymptote here. Now on the test, I'm not going to ask you to graph a function with a slant asymptote because it gets a little tricky. Well, what this one ends up looking like is, where's our vertical asymptote here? Vertical asymptote for that function. Denominator is 0. X equals 2. So we get a vertical asymptote like so. The slant asymptote is this line y equals x plus 2. So a slope is 1. The y-intercept is 2. So it looks like this. My x-intercept is when x equals 0. So what this function ends up looking like is something like this. So as x gets really big, it gets closer and closer to that slant asymptote. As x gets really big negative, It gets closer and closer to that slant asymptote. So when x is really large, positive or negative, the function is behaving like that line, y equals x plus 2. So based on that, what would you guess happens if the numerator is 2 more than the denominator? When we do our long division, we would get an x squared here. We get a quadratic asymptote. And eventually, our function gets close to the side of a parabola. If it's 3 more, then we get a cubic asymptote. And our function gets closer to a cubic function. So we can have all kinds of higher degree asymptotes where the function eventually behaves like a cubic or quartic or a quintic. So it's a kind of interesting thing that how rational functions can behave. All we're going to worry about is slant asymptotes. All right, questions? Okay. So I'm going to write up the homework, and then I want to explain our activity. Our activity has to do with graphing rational functions.
Is that for tomorrow?
No, we'll do the activity in class today. That was quite an expression of excitement.
Maddie grows. I roll my eyes.
I was telling my other class, I've told you before, we're probably canceling, not going to do Calc Camp. And I told Miss Hine, because I buy all the snacks for Calc Camp every year at Costco, and I have one of those big carts full of chips and candy and stuff. And I told her we could save money we could just do